Well, today is November 14th, and it's a snow day today. So I want to cover what we would have done in class a little bit with this video, so I'll try to do this rather quickly. But we were talking about general plane motion now. We're completing, or we have completed fixed axis rotation. So now if an object is rotating and spinning, or rotating and moving out in space, driven by some forces, you may have a force in the x direction, maybe some forces in the y, and some components that may cause some rotation, and that will cause a mass times acceleration of the center of gravity going in some direction. All right, so our equations that we'll consider are some of the forces in the x, some of the forces in the y, some of the moments about g is ig alpha. If you're going to sum moments about some other point, then this general equation applies that we talked about in translation. We'll also maybe need to keep track of our angular acceleration and how it changes relative to another point. All right. A couple other equations that we talked about or one other equation we talked about in fixed axis rotation. This is a form of some of the moments about p. Is that we can, if P, this point here, happens to be a fixed point or an instantaneous center of velocity, of zero velocity, then we can use this this form, some of the moments about P is equal to IP alpha, where P is where IP is moving the mass moment of inertia using the parallel axis theorem. So we'll talk more about why and when you use this when we come to round rolling things, but all I want to just suggest is this is another valid term or valid form of this equation if P isn't moving, or if it's a instantaneous center, which again is definition of it's not moving. And then back to the relative equation. This is our general vector form of the relative equation, but we also have the scalar form of the relative equation, which can be quite helpful and much easier to use in some cases, I believe. What we've got here is an object that's moving and rotating. It's out in space or on a frictionless surface, and we've got some forces trying to push it in one direction, forces in the x and a force in the y. So let's find out what happens. We're going to sum the forces in the x, mass times acceleration in the x. We see that the acceleration of x, acceleration of the center of gravity in the x direction is 1 meter per second, using those two forces. In the y, we only have one force moving it in the y, and we can find that the acceleration is 1 meter per second in the y direction. Find out how much it rotates by summing the moments about g and ig alpha, and we can see that there's a force. This force right here is trying to make it go in that direction. And so if I call this direction my positive direction, or the counterclockwise my positive direction, that makes this one a negative moment. And if I say that this one has this lever arm, it's trying to be in a positive direction, so that'll be a positive moment. So I got F1 is negative and F3 is a positive moment. F2 right here is actually going in that direction as well. And so that's going to be in the clockwise direction, which will be a negative moment. That's going to be equal to ig alpha. Ig was given to us there as 10, so we can solve that for alpha quickly and see that alpha is equal to 0.05. So the next thing we might want to look at, though, is what might be the acceleration of some other point. And so I'm going to define this point right up here as point B, and I'm going to go to the next page. All right, so point B is right there, and if the acceleration, or the angular acceleration, goes in this direction, and the acceleration of g goes in this direction, remember it's got a 1 meter per second x acceleration, a 1 meter per second y acceleration, so you can see that it's going up the acceleration of g is going up at a 45-degree angle. The acceleration of b, if it rotates about g, is going to have an r omega squared, which will be the normal component, and an r alpha, which will be the tangential component. And that's depicted here by acceleration of b is equal to acceleration of g, plus the acceleration of b with respect to g, that should be a g, not a c, in the normal direction, plus the acceleration of b with respect to g in the tangential direction. All right, so let's go ahead and just sum things up here. These are all vectors. There should be little vector signs above, well above that one. And we can see that we can find that there's going to be some I and j components for B, but AG has a 1 in the I direction and a 1 in the j direction. at the very beginning of the problem, this normal acceleration has that r omega squared, but if omega hasn't had time to build up anything, often that r omega squared is going to be equal to 0. The alpha term will have an I component and a j component, and so we'll say that that'll have some r alpha in the I direction. In this case, it's negative, and it'll have some r alpha in the j direction. Well, actually, it looks like that's negative too, so I made a little mistake on that. So this should be a negative, and this should be AB in the I direction plus AB in the j direction, and it'll have those two components of g in the I direction and j direction. All right, and it looks like the r alpha is going to be negative in the j and negative in the y. All right, something that looks like that. Put that to use here, and let's put that to use in this little problem here. So what we've got is we've got a beam being lifted up by two forces. I'm going to have a 100-pound force and a 200-pound force, and I'm going to try to see what happens. So all I have to do is draw my free body diagram. The free body diagram is very important, but if I say that I'm going to have some mass times acceleration of the center of gravity in the y direction, mass times acceleration of the center of gravity in the x direction, probably going to be some alpha, so I'm just going to define that. And let's just sum the forces in the x and see what we get. So sum the forces in the x is mass times acceleration in the x. So I got 200, I got that cosine component there, that's the only x force, and I get ax is 21. Sum of the forces in the y, I got that positive 100, well here we are, positive 100, got a negative mg, and I got that sine component of 200, and that gives me my mass times acceleration of g in the y direction of 26. If I want to find out how much it rotates or how fast it's rotating, sum of the moments about g usually works. And so I've got a lever arm here of 100 times that 6, which is going in that, well, see if I define counterclockwise as positive, I put counterclockwise as positive on my free body diagram. Got that negative, that's going to be in the negative direction or the clockwise direction. Then I have the sine component going in the positive direction or the positive counterclockwise direction. Both those have to have lever arms, of course, that's what a moment is. And I get my 1/12 ml squared alpha and solve that for alpha. All right, if I want to know what the acceleration of another point here, let's find out what the acceleration of A here is right there. So let's just move this up here, and I'm going to say acceleration of A is acceleration of G plus acceleration of A with respect to G. If G is moving up in this direction, in other words, it's got a Y component of acceleration, X component is going to be moving up like that. That's fine. And then we know that if alpha goes this way, then A with respect to G in the tangential direction is going to have that R alpha, which will be going straight down. All right, because it's still in the horizontal configuration. So I'm going to say the acceleration of A is acceleration of G, plus acceleration of A with respect to G in the normal, plus A with respect to G in the tangential. Now at the very beginning of the problem, this A with respect to the normal is going to be that R omega squared component pointing in, but that omega is going to be 0 at the very beginning of the problem, so I can kind of ignore that term. But I can sum all these other forces. I have an I component and a j component of acceleration of g, and then the tangential component will be negative in the r alpha and the negative in the j direction. And I can solve that for A. Acceleration of A has an I component of 21 and a j component of -20. Now negative 20, how does that work? If we look back at the picture, you can see that we're talking here now, this is the actual acceleration of point A. The actual acceleration of A seems like if you're going to lift it up, right here, you're going to make it go in the positive direction and positive direction. So it seems like acceleration of A might have a component that looks like that. But when we look at the answer, we get something negative. That just doesn't make sense. Well, what it says to me is that this is a bogus problem. This is an actual problem that cannot exist in real life. In other words, you cannot expect that 100 pounds here is actually going to lift it up. It needs more force to actually lift it up in order to make it accelerate in that way. So what I did was I changed the this is impossible. You can't have a negative x acceleration going into the floor. The floor doesn't move. So that means that this is an impossible problem. So I changed the problem to something that looks a little bit more real problem. So I'm going to change that force. Instead of 200, I'm going to make it 135. And then when I do all the math, I do the exact same thing again. Some of the forces in the x, some of the forces in the y, some of the moments about g is ig alpha. I get a new alpha. And then when I do my relative acceleration equation, I can see that with a smaller difference in those two forces, that I can actually get a positive acceleration of A in both the x direction and in the y direction. So with this set of forces, 135 and 100, I actually am lifting up the center of gravity going up in that direction. I actually am lifting up point A going up in that direction. And I still am having positive alpha. It's still rotating in this direction, but I'm actually lifting it off the floor when I get a positive acceleration for A in the y direction, which I did here. So anyway, just a little bit of insight, kind of a subtle thing here, where sometimes the book will give us problems that actually don't make any real life sense. This one, with these sets of forces, does make some sense. Okay, they actually can, they actually can lift it up off the ground with that. Here's another little problem that we've got a stick here that's being excited with a force. I'm going to push it this way, and it's going to cause this thing to rotate in this direction. And you can probably see in your mind what's going to happen. That's going to move this way. After a very short time, the stick is going to be at an angle, then it's going to be at a steeper angle, and after a while it may have an angle like that. So let's find out what happens. What we're looking for is the acceleration of A. So if I sum the moments in there, or some of the forces in the x, and some of the forces in the x is mass times acceleration in the x, what I end up understanding is that there's a mass times acceleration of vector of the center of gravity in the x direction, a mass times acceleration vector of the center of gravity in the y direction. I'm going to have that pushing force. AX would be maybe some friction or something like that. In this case, it's 0, but there may be a reaction there at y. But what I can do is look at all the forces in the x direction. And it's really only that one. That's the only one I've got, and that's going to cause a mass times acceleration of the center of gravity in that direction, which I can solve for right there. Now, the moment equation, if I want to know what my alpha is, the alpha is going to be in this direction, like that. And I can find out what that might be by some of the moments about center of gravity, which I've done. And I can find that alpha is equal to 144 radians per second. Now, to actually find out what the acceleration of A, which is what our problem is, what's the acceleration of A, I'll need to use something relative. So let's do a relative equation. I like the scalar way easier. So acceleration of A is acceleration of G. Say A with respect to G in the normal, A with respect to G in the tangential. And we're going to discover that at the very beginning of the problem, the r omega squared component is 0 because omega is equal to 0. So there is no normal acceleration, but I still do have that r alpha term. I'm going to have acceleration of G in the x direction, which I've got. And if you look carefully at the picture, A can only accelerate in the x direction. It's not going to levitate. There's nothing going to lift it up, and it's got a wall here or something that's going to keep it from going down that way. So the acceleration of A only goes in the x direction. All right, so with that, then let's just put our terms in here. We got acceleration of A in the I direction, acceleration of G in the I direction, plus an r alpha in the I direction, and I get that as 193 feet per second squared. All right, so I can also do this with the relative equation if I wanted, and a relative vector equation, and I can get the same thing. All right, the last little problem that is kind of clever is something that's probably pretty realistic, really, is that a beam could be trying to be supported by a couple of strings here, and one of them breaks, and then figure out what happens. Well, let's draw a careful free body diagram of our beam. As soon as the string breaks, we got a beam, and we got a tension in that string, and an mg coming out of there. And that's the only forces that we can see on this beam. And when that happens, what's going to happen? Well, it's going to start dropping. The center of gravity is going to start dropping, so that we've got a mass times acceleration vector going that way. It's going to begin rotating in this direction, so it's going to have an alpha in that direction. If we look at the forces carefully, there are no forces in the x direction. I don't see any forces. The only forces I see is that t and that mg. Those are the only forces there, so I can sum the forces in the x direction, and I get everything is equal to 0. In the y direction, I got a t minus an mg, and I have a mass times acceleration of g in the y direction. I've defined up as positive, and positive in the x. So when I drew that vector, it's going in the opposite direction of positive, so I have to have that negative sign right there. Over here on G, some of the moments, I can sum the moments about center of gravity, and if I do that, then the only force I've got is that tension is causing a moment in this direction. And if I define positive going in that direction and positive going there, I can see that alpha is equal to 3t over ml. All right, so I've got 2 equations and 3 unknowns. I'm going to need another equation, and so we're going to use the relative equation for that. Acceleration of g is equal to acceleration of a plus g with respect to a in the normal, g with respect to a in the tangential. All right, if we look carefully at the picture and look carefully at the equation so far, if the acceleration of g in the x direction is equal to 0, g can't accelerate in the x, then there's no way that a right here can accelerate in the x as well. So in other words, there's nothing accelerating anything in the x direction, therefore acceleration of a in the x direction is equal to 0. How about in the vertical direction? If you notice here that this wire is stiff, or it's not stiff, but it's tight. It's got tension in it, and but it's not pulling it up. It's just holding it up. So it's not pulling the point A moving in the other direction or moving in the y direction. It also isn't allowing it to move in the x direction or move down below. So we can conclude just by observation that the acceleration of A in the y direction is also equal to 0. So acceleration of A is equal to 0. And if I just plug those into my equation, then I can solve this for AG is equal to L over 4 times alpha, and plug that into my equations, and I can then see that tension is equal to this 4/7 mg. You can do the arithmetic and just verify that. Anyway, that's what we went through in class, and I hope that this will help you with your homework.